In this session, we'll talk about relative extremum. First, let us see the definition of relative maximum. We say a function f from interval I to R have a relative maximum at C belongs to I if there exists a neighborhood V delta C, which is open interval C minus delta to C plus delta of C, such that for all x in V delta C intersection I, fc is greater than equal to fx. That is, the function f have relative maximum at C if we can find a neighborhood V delta C such that for any point x belongs to V delta C and I, f has a maximum value at C compared to all other values. Let us see an example. Consider the graph of the function fx defined on interval I, which is closed interval 0 to 5, given in the following figure. So you can see this is the graph of function fx in interval 0 to 5. The function has relative maximum at c is equal to 1. Because taking delta is equal to 0.3, we see that in neighborhood v is equal to open interval 1 minus 0.3 to 1 plus 0.3, which is equal to 0.7 to 1.3, the function has maximum value at 1. So in this neighborhood, we can see at x is equal to 1, f has maximum value. That's why we say function has relative maximum at c is equal to 1. Also using the same reasoning, f has relative maximum at c is equal to 3.5 also. Because around 3.5 also we can find a small neighborhood in which the function will have a maximum value at point 3.5. Now let us talk about the definition of relative minimum. We say a function f from I to R have a relative minimum at C belongs to I if there exists a neighborhood V delta C of C such that for all x in V delta C intersection I, fc is less than equal to fx. That is, f has a relative minimum at C if we can find a neighborhood in which for all points x in that neighborhood and the interval, f has minimum value at C compared to all other values. Now consider the example, consider the graph of the function fx defined on the interval I is equal to close interval 0 to 5 given in the following figure. So this is the graph of the function defined in the closed interval 0 to 5. The function has relative minimum at c is equal to 1. Because taking delta is equal to again 0.3, we say that in neighborhood v is equal to 1 minus 0.3, 1 plus 0.3, that is the neighborhood which is an open interval 0.7 to 1.3, the function has minimum value at 1. So in this interval, you can see the function have f value at 1 is minimum. So we say f has relative minimum at c is equal to 1. Also using the same reasoning, f has a relative minimum at c is equal to 3 also. Because around x is equal to 3 or c is equal to 3, we can find a small neighborhood in which at the value of function at 3 is minimum. Now we say that f has a relative extremum at c belongs to I if it has either a relative maximum or a relative minimum at c. So if function f has having relative maximum or relative minimum at c, then we say it is having relative maximum, relative extremum at c. Now let us talk about interior extremum theorem. The statement is, let C be an interior point of the interval I at which function f from I to R has a relative extremum. That is, C is the point of the interval I at which f has relative extremum. If the derivative of f at C exists, then f dash C is equal to 0. So if the derivative of f at c exists, then the derivative of f at c, the value will have 0 value. Let us see the proof. We give proof for the case when f has a relative maximum at c. The proof for the case of relative minimum can be proved similarly. Now let us consider if f dash c is greater than 0. We have to prove f dash c is equal to 0. If possible, let f dash c is greater than 0. That is, if limit x tends to c fx minus fc upon x minus c is greater than 0, because this is the definition of f dash c, so this is greater than 0, then there exists a neighborhood v of I of c. So we can find a neighborhood v of I, v contained in I of c, in which this expression fx minus fc upon x minus c is greater than 0 for all x belongs to v and x is not equal to c. Now if x belongs to v and x is greater than c, then we have fx minus fc, which can be written as fx minus fc upon x minus c, which is a positive quantity, and x minus c, which is also positive because x is greater than c. So we get fx minus fc is greater than 0, which implies that for x belongs to v with x is greater than c, fx is greater than fc, because fx minus fc is greater than 0 implies fx is greater than fc. But this contradicts the hypothesis that f has a relative maximum at c. Because if f has a relative maximum at c, then in the small interval v, fc is the maximum value. Thus, we cannot have f dash c is greater than 0. Similarly, we cannot have f dash c is less than 0. We can prove similarly. Therefore, we must have f dash c is equal to 0. This completes the proof of the theorem. Now let us take this corollary. Let f is a function from interval I to R be continuous on the interval I, and suppose that f has a relative extremum at an interior point C of I. Then there will be two cases: either the derivative of f at C does not exist or it is equal to 0. Because in previous theorem, if we have seen that if the derivative exists, then it is equal to 0, or the second case may be the derivative does not exist. Let us see this with an example. So it is a form of remark. Note that if f dash fx is equal to mod x defined on interval I, close interval minus 1 to 1, then f has an interior minimum at x is equal to 0. You can see at 0 it is having interior minimum. However, the derivative of f fails to exist at x is equal to 0. Thank you.